Hello and welcome to this recorded e-learning about FPGA power management HDL coding techniques. My name is Frank Nelson. I'm a Xilinx technical trainer and course developer. I'll be your instructor for this module. Our objectives for this module are for you to be able to explain how power is dependent on the HDL coding style that you use, be able to describe how your design's power consumption is dependent on your use of control signals, explain how some common design techniques can improve your design's power consumption, and be able to show how some common design techniques can improve your design's power consumption. Well, first of all, the block RAM, if it is enabled at all, will always be consuming power. Now, there is a temptation by our designers to always just leave the enabled tide high. You may not be aware, but it is consuming lots of power if it is enabled, even if you're not changing the address. So, if you're trying to reduce your power, one of the first things to consider is to remember that the block RAMs do consume a significant amount of power, and you should use the enable functionality to save that power. Now, what we're talking about in this example is segmenting the memory space of multiple block RAMs such that only one is activated at a time. Now, this reduces power by about 75%, although in a high-speed application, your performance might take a small hit. So what is done is that rather than segmenting the memory across multiple block RAMs so a read or a write is done in parallel, now only one block RAM gets used each time. Now, to build this, you'll use the Xilinx core generator. After customizing the memory with the GUI, you'll simply select the low power option that is now available in the GUI. The net list of the memory blocks will be made, and all you'll have to do is instantiate the top level memory component into your design. If you're building a small memory, that's a memory less than 4K bits, you can build it efficiently using lookup tables. Larger memories, that is larger than 4K bits, and it makes more sense to use the block RAM resources because the speed gets prohibitively slow when targeted to LUTs. But this will depend on how many block RAMs and how many LUTs you have available to you. If either resource is limited, you may be forced into using the other resource. But when designing for minimal power, smaller memories use less power when you use LUTs. Most designs do not need a global reset in an FPGA because on power-up, a reset is completed automatically. ASIC devices usually design global resets out of habit. If you're coding a global reset into your FPGA design, you're actually coding in a second global reset. The FPGA's global set reset net, that is the GSR, is accessed with a startup block. Now, to learn more about that, check out the Xilinx Unified Libraries Guide for more information. This GSR will give you access to the ability to activate a global reset whenever you desire. But note, this routing is slow, and its timing is uncharacterized. It is not recommended that you use it unless you're prepared for poor global reset timing. Local resets can be built at your discretion, although Xilinx recommends that they be synchronous and managed by the designer to minimize the number of control signals you have in your overall design. It should not be necessary for you to use the GSR to build a global reset. It is actually discouraged due to its slow performance. But some customers use it to save routing an additional high fan-out reset on general interconnect. The GSR uses dedicated routing resources, so it prevents routing congestion, and it can be used to reset the FPGA to a known state chosen by the designer. So not every resource has to be a 0. Now that is done with the init attribute for each flip-flop. The GSR has access to an OR gate that connects to each flip-flop. That allows each flip-flop to not only have access to a local reset, but the GSR as well. Initialization of flip-flops in an FPGA is important for behavioral simulation. In this example, we have behaviorally coded to reset in our HDL. This will allow the simulation to show clearly what condition each flip-flop is in after power-up. Now, synthesis tools will react on this code. Most people assume that this is unsynthesizable code, but it will affect the init value of the registers because that is tied to the register's primitive. The code in this example will reset to a 0 when the GSR is released after configuration. This way, you can have a known value in your chip each time you configure the FPGA. This code will simulate to a 0 for fast startup during a functional simulation. If you do not do this and you have a counter, you'll have X's counting +1, and all you will see during simulation is an X counter. But if you use this, it will start with a known value. Now, this is mandatory if you design without a reset on the circuit. Inferring an initial value only works for data types of standard logic, bit vector, bit, but does not work for integer types. Now note that this inference is currently not supported for Spartan 6. There is no reset functionality built into the shift register LUT. If you have a reset on the shift register you code, the synthesis tools are left with one of two choices. They either do not infer the shift register LUT, meaning they will use a bunch of CLB registers, which is not what you want, since that will waste CLB flip-flops and increase the size of your design, or they will try to emulate the reset. Emulating the reset means that they add more logic and it becomes even slower than it should be. In one customer design, there was a global set reset throughout everything, and the known shift registers could not be connected. The designers were already inferring about 100 shift register LUTs and were doing a good job making use of the dedicated resources. But by removing the global set reset, they obtained over 150 shift register LUTs. This, of course, saved powers and saved CLB flip-flops. It is important to remember that the DSP slice and block RAM resources only use a synchronous reset, so if you code for an asynchronous behavior, your synthesis tool will not be able to infer the DSP slice or the block RAM. Now this will hurt your performance and increase your power consumption significantly. Taking advantage of the dedicated hardware resources like this is going to provide extra slice resources, which will also give the tools the ability to reach a higher design speed as well. It is important that you manage the number of control signals your design uses. Xilinx has not recommended that you don't use clock enables. In fact, designing synchronously is critical to your success. Xilinx recommends that you try to reduce designing low fan-out clock enables, that is, clock enables that drive fewer than 8 registers. You also should not use global synthesis switches to turn off the use of clock enables. This will increase the size of your design dramatically. You should also be aware that how you code for the clock enable can control whether the clock enable is connected to the clock enable port of the flip-flop or driven to a LUT input. Recall that the clock enables that drive the control port of the flip-flop are considered a control signal, and that requires that the registers in the same CLB share the same control signals. So, usually, for the lowest fan-out clock enables, it's better to drive a LUT input, especially if your design has a large number of control signals associated with it. For more information about the proper use of XST and good HDL coding techniques and proper timing constraints, check out the XST user guide for Vertex 6 and Spartan 6 devices. In summary, we want to encourage you to code properly to minimize the power of your design. First of all, only enable block RAM use during active read or write cycles. Use low power architecting for multiple block RAM arrays. That's the example where we looked at the core generator usage. Build small memory blocks with LUTs if they're less than 4K bits. Minimize your local resets if possible. Keep in mind that no reset is best since the FPGA gets a global reset automatically. This allows inference of the shift register LUT. Design with synchronous resets. This enables inference of the DSP slice in the block RAM output register, which is good for performance. Don't build a reset into your design for simulation purposes. Instead, code for the init behavior. And then you control the use of clock enables. Well, there are a lot of places to learn more about FPGA power consumption, and they all start at support.xilinx.com. But we wanted to point out to you that the Spartan 6 FPGA Power Management User Guide is a very worthwhile resource for learning about the higher-end functionality of these newest devices and how they can save power. We also recommend you refer to the power consumption in 65 nanometer FPGAs. That's white paper 246, and that'll give you a lot more information, technical information about how the silicon goes about managing your power consumption. If you'd like to see what other courses we offer or what other free RELs are available to you, go to the education link you see here. We want to point you directly to the Spartan 6 and Vertex 6 device families course, which discusses everything you need to know about these device families in one course training. We also have a number of other RELs that go into power management, power estimation, Spartan 6 and Vertex 6 power management features, and also try and answer very common questions about power management design techniques. But before you do anything else, please take a second and let us know what you thought of this REL. Just click on the icon at the top of the page and tell us what you thought. Again, my name is Frank Nelson. You've been listening to the What Are Power Management HDL Coding Techniques REL. Thank you for listening, and thanks for your business.